Got some quite interesting news to tell you. We're ahead of schedule, which is good. Today, the first part of today, I'm going to finish off 9.1, and then we will start 9.2, which is our last section. And 9.2 is called the dot product, I believe. And we'll look at how to find angles between two vectors and so on. And that's it. So
9.2 is our last unit?
I believe so, yeah.
We still have 2 weeks till the final. It's kind of weird.
It is. It's surprising. I don't know what's happened, but I'm happy. The last one will take a little bit of time. So I had planned to have a couple of days next week, which is what would have been in my schedule, to revise for the final. But it might be that we'll have even more than that. We have 3 days, which is always good. Nothing wrong with that, right? More time to get ready. Anyway, let's get started. Today and probably the rest of what's left of Vectors, chapter 9, is going to look like I'm a physics professor. So we are going to deal with resultant forces and some aircraft questions. So these are all the questions at the end of section 9.1. So let's do an example of what would be called a resultant force. I want to do 2 of those. We've already touched on them last time, but just going to make them a little bit more a little bit different each time. Okay, so in this story, you're going to have a force pulling in this direction. I'm going to call this vector U. And you're told that the magnitude of this force was 10, and that the angle that it makes with the x-axis is 30 degrees. And then you're given a second vector, which I'm going to put up here, I think. I'm going to call that vector V. And the magnitude of that vector is going to be 6. And the angle that's here is also going to be 30 degrees. And if you were asked to find the resultant force, what we're expecting you to do is to find out what the vector U is in component forms and find out what the vector V is in component form, but no decimals, not yet. All you're going to do is find their exact values. And the reason I know that, well, a couple of reasons. One is these angles live inside the unit circle. And secondly, the question, if they wanted you to do everything from start to finish as decimals, they would mention, give your answer to 2 decimal places. That would be the clue. So let's start with the vector U. I need to find what is called its x component. And I need to find its y component. And the formula for its x component is the magnitude of U cosine of the angle it makes with the x-axis, and it's the magnitude of U times the sine. Okay, nothing too surprising here. So x component is going to be 6 times the cosine of, I'm saying 6, I'm looking at it wrong place. It's 10 times the cosine of 30 degrees. And the y component is going to be 10 times sine of 30 degrees. And if we look at our unit circle and we look at 30 degrees, the cosine is the x coordinate. So that's 10 times root 3 upon 2, which simplifies down to 5 root 3. And the sine of 30 degrees is a half. So that's 10 times a half, which gets me 5. So I now know what the component of the vector U is. But we'll box around that to remind me. And then we go and we find V. And same thing. For the vector V, the x component is going to be the magnitude of V times the cosine of the angle it makes with the x-axis. The y component is the magnitude of v times the sine of that angle. In this case, it's 6 times the cosine of somebody and 6 times the sine of that somebody. And what you have to realize that in these questions, the angle they give you doesn't necessarily mean it's the one that is there, because we always measure angles from the x-axis, but from the positive x, from here. Would you agree that's 150 degrees? Agreed? 150. So this is going to be 6 times the cosine of 150 and 6 times the sine of 150. So I go over here, I find 150. The cosine is the x coordinate, and that becomes -3√3. And the y component in this case is a half again. So the vector v is going to be -3√3, 3. So when you're being asked to find the resultant force from a picture where there's 2 or more vectors pulling from the origin in different directions, as they are here, with different amounts of force as well, this is v and this is u. And then the resultant force which is why this feels like a physics class, is you add the 2 vectors together. So in this case, it's going to be 5√3(5) added to -3√3(3). And that guy leaves me with 2√3, and that guy gives me 8. And that's the resultant force, which I'm going to call W because I don't want to have to keep writing resultant force all the time. So far, so good. Resultant force. Now, you could be asked, and they do in the question I'm looking at, which says something like this. I'll just write it down because if I say it, it won't stick in your head. It says find the additional force if any, which I don't see why that needs to be there, for the forces to be in equilibrium. And they mention 2 decimal places. Okay. Actually, the answer up here, they wanted it in 2 decimal places as well, but I like the answer there. So if I return to my picture, if you add these 2 guys together, the resultant force is roughly 2 and that and 8 up. So it's about this direction here. So if you combine those 2 forces, this single force W, where my pen is, would be the equivalent. Now this thing here is actually very easy to do. The answer is that. If forces are in equilibrium, it means that when you add them all together, you get the 0 vector. So if these 2 forces combined give me this, wouldn't that be the other guy? So that when you add this to the last piece of the puzzle, right, the additional force, won't this one and this one cancel each other out and you've got a balance? And so in other words, if you pulled in that direction and You pulled in that direction, analogy. Can you imagine there a guy standing at the center and there's a person pulling him this way, a person pulling him this way, and a guy down here pulling him this way? Wouldn't this guy here, if it was an equilibrium, wouldn't the guy stay put? The guy trying to pull him up would get balanced by the one guy, but he's pulling a lot harder right downwards. So equilibrium is, the forces are all balanced, right? So whatever you get to this answer, if they ask for an equilibrium, just find the negatives of it and you're good. So it's easier to talk about that one than it is to do that one. So I wanted to do 2 of these resultant forces. That's the first one. And here's my second one. And it's really the same idea. Only difference is there are going to be 3 of them. And this is a version of question 28. So I'm going to have a force pulling in this direction called vector F1. I'm going to have a second force pulling over here. It's going to be called vector F2. I'm going to have another force over here. It's going to be called vector F3. In this picture, that angle is 60 degrees. This angle here is 30 degrees. And this angle here is 20 degrees. Now, they already tell me in the question that they want the resultant force as a decimal. And I know, even if they never told me that my answer is going to be in a decimal. Because would you agree that 20 degrees does not fit in a unit circle, right? So that means I can do these guys to, what are they, 2, so I'm going to do everything to 3. Okay, so first thing I'm going to do is find out what F1 is. It's X component. And that's going to be, oh, I forgot to tell you the magnitude. This one is 15. This one is 12. And this one down here is 9. And so it is going to be magnitude 15 times the cosine of 60 degrees. So Y component is going to be 15 times the sine of 60 degrees. And since we're working with decimals this time, I don't need to use my unit circle. So 15, oops, clear. Yep, almost caught there. Remember, it's degrees in this question, so make sure you're working on degrees. So 15 times a cosine ends up being 7.5. 15 times a sine. And
I'm going to tangent on accident.
Whoa, well caught. No, they're right next to each other. Well, not that next to each other. 15, thank you for catching that. 15 times sine of 60. And okay, 12.990. 990. That's F1 done. So it's going to be a 7.5 and a 12.990. I'm going to do the same with the other 2. So that's this one. X component, Y component. In this case, it's going to be 12 times the cosine of some angle and 12 times the sine of that angle. But we already did this guy like 5 minutes ago. This angle that we're going to use is not 30 degrees. Would you agree it's 150? Right. So 150, 150. 12 times the cosine of 150. Don't like the answer, but it is what it is. Negative 10.392. And this guy is going to be 12 times the sine of 150. That's a nice answer. So our second vector F2 is negative 10.3926. Put a little box around that to remember who he is. And our final guy, F3. Well, what do we have? X component again, Y component. This time it's going to be 9 times the cosine of some angle and 9 times the sine of some angle. What angle will we use for the vector F3? It's not 20 degrees. What angle will we use for F3?
200.
200, right? 180 plus 20 more. Over here, 9 times cosine of 200, negative 8.457, and 9 times sine of 200 is negative 3.078. We are, oops, we're almost done. When you're doing these kinds of questions, it's a good idea just to do a very quick check. This vector here, F1, 7 and a bit by 12 and a bit. That makes sense, right? It's pointing in the right direction. The second one is negative 10, 6. Would you agree? Negative 10 up 6, that fits. Isn't F3 negative something, negative something? You see it fits. So if one of these was a plus and I can look at the picture and I realize it's not that number, right? It's in the second quadrant and I can clearly see it's not. Then you might want to check maybe your angle's wrong. Maybe you were in radians instead of degrees. Something like that may have caused a problem. Now you want to find the resultant force. You just add them all together. So it's going to be this fella plus this fella plus this fella, which I don't have room for. So I'm going to my calculator and I'll type in the x's first. So 7.5, take away 10.392, take away 8.457. And the answer I get is negative 11.349. If I do the y's, it's going to be 12.990. I think I screwed up. No, I'm good. Looks like I did, but I didn't. Add 6, take away 3.078, and I get positive 15.912. So there is your resultant force. So according to this, if you combine these three forces, you're going to go 11 to the left and 15 up. So it would be pointing somewhere like that. I could imagine that. Aren't there more forces this way than against it? So yeah, it seems reasonable. And then you want the balance force. What did it get? Yeah, what additional force? Right, so that's the answer to A, the resultant force. What would make it an equilibrium? Well, just like we did last time, So you just
be positive 11.
Yeah.
Yeah, that one. What you
that
just
one. So you just switch your signs. So the second answer is pretty obvious. If you know the first one, the second answer, the equilibrium force is basically the negative of this one. And that is finding resultant forces. Any questions about that? Right. I mean, once you've seen a couple, you've seen them all, right? Let's move on then and do an aircraft question. And the aircraft question, there are two of those. So one of them's 26 and the other is 27. And they are pretty similar to what we've done, but you don't get a picture, and the final answer is going to be written in a slightly different way. But let's see what we've got. A pilot heads due east. Okay, so I'll put my axes in first. And anyway, a pilot is due east at 450 miles an hour. So he's going this way. What am I going to call this guy? I'm going to call him U. So U is the jet. And since he is going 450 miles east, can't we just write the components of that without doing any math at all? Because due east is that. Are you comfortable with the mileage is measuring the magnitude, so 450, 0. And the wind is blowing. And the wind is blowing north. I've got a feeling, did I do this one yesterday? No, okay. Then the wind is blowing due north at 40. So can you imagine that this is the wind? I'll call that V. And its speed is 40. So the vector for V would just be 0, 40. Are we cool with that?
So are these magnitudes that we're dealing with right now?
Yeah, the magnitude
would they technically have the line, right? The lines on them?
Yes, it has a line because the line is 40 units long, representing 40 miles.
When representing the line of view or the vector of view, would it have the two?
Oh, like the absolute value.
Yeah.
Oh, yeah. If you were wanting to, if you were saying what that fella, if they weren't telling you in English, they would have said that this guy was 40, the magnitude was 40, and they would tell you that this guy here is 450.
Right? Oh, gotcha. Okay.
Right. But in the context of an aircraft kind of story, they talk about the speed. So think speed is the same as the magnitude, right? If you're going 50 mile an hour, your vector is 50 units long, right? Think about it as speed is telling you the magnitude. Now, if you're doing a jet and the wind, the real direction that the jet is going to go is roughly about that direction, agreed? The wind's going to blow them off course, and we can find out what that is as a vector by adding these together. And that's 450, 40. Excuse me. Now, we've already answered question A, which is this guy, and question B, which is this guy. Question C doesn't ask, does it? Yeah, it does. Question C asks for the vector for the aircraft. So that's this fella. And then question D asks for the speed of the jet. Now, this is the direction that the jet's traveling in, right? When you compensate the wind and the jet flying east, this is actually the true direction it's going. speed is a scalar. That means it's a single number, it's not a vector. That is a vector, that's velocity, but we want speed. What do we do to this vector to find out the speed?
Aren't we finding the magnitude of it?
You are. That's the answer I wanted to hear. Right. And so the magnitude of that is going to be the square root of 450 squared plus 40 squared. And did they mention decimal? Yeah, to the nearest integer. Okay, so they want a nice whole number. That's going to make my life a bit easier. Square root of 450 squared plus 40 squared. And the answer to the nearest whole number is 452, and that's going to be miles per hour. And then they don't ask for angle theta. So if I draw a little baby picture of what we've got here, this is the aircraft. They do not want to know that angle, which is what you would typically be asked to find, right? What angle does this vector make with the x-axis? Because this is aircraft and ships do the same thing. Ships measure direction, not the way that we do in math from the x-axis going this way. They measure the direction of how many degrees away from north you are. So the angle that they actually want us to find is that angle. Does that make sense? So you might say, I'm going 5 degrees east of north. Right. That means you're not going true north, you're going to be 5 degrees, towards east. Couldn't it be 80 degrees east to north, which would be almost east, wouldn't it? You'd almost be at the east. So bear that in mind. So we're going to still find this angle theta first. And let's pretend it's 20 degrees. If it is 20 degrees, won't the answer to E be 70? And if it's 10 degrees, won't it be 80? And if it's 49 degrees, it'll be 41. So we're still going to find theta the way we always did, but then we're going to do one extra step. We're going to find out what this angle here is. So to remind you how you find the angle.
Can you move your paper up a little bit?
There we go. The formula for calculating the angle that a vector makes with the x-axis, the guy we call theta, it's the inverse tan of the y component divided by the x component. And yesterday, when we did that same kind of question, we got the ugly one, which was the answer that the calculator gives you might not be the angle that you need. But in this case, we're going to get lucky because it is the angle that we need. So inverse tan of 40 divided by 450 comes up with 5 degrees. Wow. But what is our angle? This is 5 degrees, but what's our angle? This fella here. If this is 5, how much is that?
85.
85. So you will write down 85. I think they have north, 85 east. That's just the letters around it. But you only need to put the 85 part in. Are we good with that? It's kind of similar to what we did with the forces. I think the only major difference is here that we didn't have a lot of calculations for U and V, but we did have to find an angle and then compensate because of the direction thing. Do you want to see another one of these ones, or are we good?
Sure.
Okay, so the other one is 27. And you've got north, which is our y-axis essentially. And you've got x, which is our east one. And a jet flying through a wind that is blowing with a speed of 55 miles an hour at a direction north E 30 degrees. So they're telling me that the wind is going this direction and that that angle there is 30 degrees. This is going to be the wind. And the wind has a speed of 55. The jet has a speed, so the jet is going this way. And it has a speed of 765 miles an hour. And the pilot heads the jet 30 degrees this way. And the jet was what again? 765, it was to my question. So we are going to find the speed of that jet and the direction of that jet. But before we do that, we're going to have to find this vector, which I'm going to call U, and this vector for the jet, I'm going to call that V. So for the vector U, the X component is going to be the magnitude of U, cosine of its angle. And the Y component is going to be the magnitude of U times the sine of that angle. The wind has a magnitude of 55. And we have to decide what angle goes here. The magnitude of the wind is 55. And we have to find the angle. And hopefully we've done this enough times that if that's 30, would you agree this angle, the one we're really going to use, is 60? That seem reasonable? So I'm putting 60 in there. There. And we're going to be working with decimals here, so that's fine. 55 times the cosine of 60, 27.5. And 55 times the sine of 60, and that's going to be 47.6. So the vector U in its component form is that guy and that guy. And we're going to do the same for the vector V, the jet. And the X component of it is the magnitude of vector V times the cosine of the angle it makes with the x-axis. And the Y component is going to be the magnitude of the vector V times the sine of the angle it makes. And the magnitude in this case is 765 times the cosine, some angle, and 765 times the sine of that angle. Okay, this picture's getting really messy, but one last thing to do. If you do that angle there, which is the angle that you should use, that's the one it makes with the x-axis. How big is the angle for the jet?
Is that 120?
So you put in 120 here, put in 120 here, and move on to the calculator. So 765 times a cosine of 120 gives me negative 382.5. And 765 times the sine of 120 gives me the answer 600 and suppose in it, yeah, okay, 662.5. So the vector V is negative 382.5, yeah, by 662.5. Okay. all that we've done right now is get the things that you need to answer the question. And the question is, what's the real speed going to be for this jet? Which is, what's the magnitude of this vector? Not this vector, sorry. First, we have to add them together, the resultant vector, and then we do it. So you're going to add this guy to this guy. So let's see what that looks like. 27.5, take away 382.5, and that's negative 355. And then if you combine these together, you get 47.6, add 662.5, and I make that guy 710.1. So that's the resultant force. So the aircraft's probably going like that. The speed is going to be the magnitude of that vector. So it's the square root of this guy squared plus this guy squared. Square root of negative 355 squared plus 710.1.
That's not gonna work because of the parentheses around the.
Oh,
350.
let me take it again. I need a parenthesis for the first one, but I better make sure that I finish with the right one. The faster I go, the more mistakes I make. We got negative 355 squared. That's good. Plus, don't really need one for the second one because it's positive. Squared. Just make sure I finish with a bracket. There we go. So it's going to go 793. What do they want? 1 decimal place 0.9 miles per hour. So all that work was just to find out the speed. So let's see what the original speed was. 765, and it's going to go at a little bit faster. So I guess the wind's helping it a little bit. Now, to get the angle, which is the last part of the puzzle, right, we're going to do theta is the inverse tan of the y component over the x component. So theta, which is the angle that you make with the x-axis, is going to be 710.1 over negative 355. Let's see what that looks like. Pretty sure that's going to be an awkward answer. 710.1 divided by negative 355. And yep, the answer I get is negative, one decimal place, is negative 63.4 degrees. Now I know that our guy is up there somewhere, right? And that ain't that number. If I try to draw where 63.5 is with a negative, it would be here, right? Don't I need that angle? In fact, don't I need that angle? Right? So what would the real value of theta be? Because that's not the one I'm going to use, right? I need
Add 180.
Yeah, add 180. That's happened before as well. So I'm just going to go add 180 since it's in my calculator. And that's going to be 116.6 degrees, and you're really happy. And then you put it in the book, and WebAssign tells you you're wrong. So let's try and show you why it tells you wrong. You've just found out, quite correctly, that the angle I've just drawn is that one. But this is an aircraft question.
Yeah, I assume it wants it from north.
They want it from north. So if you want to get it from north, don't you subtract 90 from it? So you have to play about with the number, right? Because to get that angle, isn't it 116 point thingy, take away 90, which is 26.6 degrees. So we had to play about with the answer that we got wasn't usable. We turned it into one that was usable, and then we found out that that's not the number they wanted, because when you do journeys, they measure direction of how far away from north you are, or I think in the other direction, how far away from south you are. Are we okay with that question? Let me move on then. Our last topic from our last section. We are almost done.
Is 9.2 gonna be on this week's test?
No, it'll be on next week's.
Perfect.
So, because you'll need, next week's test is going to be dead easy in the sense that there's only one thing you need to study for, which will be this section that we're about to get started today. I think it's 9.2. I don't see why it shouldn't be called 9.2. We're going to look at a thing called the dot product. Okay. Suppose we have two vectors. I'll call the first one u, and it's going to have components u1, u2. And I got a second vector v, and it's going to have components v1 and v2. The dot product, written down as u, big noticeable dot v, is given by this formula. u1, v1, add u2, v2. No. Can you see why the word product is in the name for this thing? Don't you multiply things, which is what a product is? I'll give you an example. Suppose I have a vector u, and it's 5, -3, and I have a vector v, and it's 2, -1. If you were being asked to find the dot product of u and v, it would be 5 times 2 plus -3 times -1. And it would be 10 add 3, and the dot product in this case would be the number 13. Now, we're not telling you yet why you would want to find the dot product, but later on, you're going to find out that you can use it to tell the angle between two vectors. So one of the major uses, not the only use, but one of its major uses is to allow you to tell the angle between two vectors. Can you imagine this is the vector u, and this one here is the vector v? When we talk about the angle between them, we mean that angle there. And that is very often quite a useful thing to know about vectors, right? Essentially, how far apart are they pulling each other, right? Here are two vectors. Don't look anything that special about them. And I'm going to calculate their dot product. And that's 3 times -2. Actually, can I change that to 2? Yeah. 3 times -2 plus 2 times 3 and the answer you get is 0. So far, so good. Now, third situation. Let's make that -2, which is what I kind of wanted the first time. If I do the dot product this time, I get 3 times -2 plus -2 times 3. And the answer I get is -12. What this shows us is that a dot product can be a positive number, it can be a negative number, and it can also be 0. The value of a dot product can give you information about how big this angle is. If the dot product is a negative number, the angle theta is bigger than 90. If it's a positive number, the angle theta will be less than 90 degrees. And if the dot product is 0, theta will be 90 degrees. So you can tell from the dot product of two vectors in a very rough way whether the angle between them is less than 90, acute, bigger than 90, obtuse, or an exact right angle, could be at corners like that, 90. Any questions? Are we still good? Okay. There is a second calculation that you can use. I'll call them U and V. Let me stick to my system. There is a second calculation for dot products. You can find it by taking the magnitude of vector U times the magnitude of vector V times the cosine of the angle between them. So if I give you two vectors, let's say I give you a vector U, I give you another one, vector V, angle between them is theta. The dot product will be the length of U times the length of V times the angle in between. So imagine I told you that vector U went in this direction, and I told you its magnitude was 10, and I had another vector V, this guy here, and I told you that the magnitude of V was 15, and I told you that the angle between them was 35 degrees. Then you can get the dot product. It's the magnitude of U times the magnitude of V times the cosine of the angle between them. So it's going to be 10 times 15 times the cosine of 35 degrees. Now, if this angle is in your unit circle, you would do that as an exact value. If it's an angle that's not in your unit circle, then you do it to whatever accuracy they ask for. So let's say it's 1 decimal place in this question. So you go 10 times 15 times the cosine of 35 degrees. And I get that the dot product here is 122.9 to 1 decimal place.
So this is just another formula to find the dot product?
Yep, right now it is. It depends on what they give you. See, if they tell you U and V like this, won't you use this formula to get the dot product? But if they tell you the formula in terms of what the magnitude of UV is and the angle between, then you can use this formula, right? So if I give you particular information, sometimes you'll use, multiply them together guy. Sometimes you'll use this guy. For example, suppose I asked you to find the dot product of these two vectors. And I will use A and B just to be different. If I asked you to find the dot product, which formula would you use in that question?
The first one we talked about.
Right, so you would go 1 times 3 plus 7 times 5, right? And you get 3 and 38, I think that's. On the other hand, if I gave you a picture or I just told you that, right? Sometimes they more likely draw a picture, but if I just told you that, wouldn't you use our dot product that looks like this guy? And although the formulas are quite different, they both give you the dot product. So this would be 3 times 2 times cosine of 15 degrees. I guess since I've started it, I should finish it. So 6 times cosine of 15. That's about 5.8. Now, the real cool thing is when you put both formulas together. So let's show you how that works. U dot V, right, is made up of U1 V1 plus U2 V2 plus U3 V3, right? The dot product is also the magnitude of U, the magnitude of V, and the cosine of the angle between them. Now, since these are both the same thing, that makes these two things the same. And so I now know that those 2 times cosine theta must be the same as this. And if I wanted to get cosine of theta, then wouldn't you divide both sides by these two guys? And what we tend to do is, this horrible mess is kind of ugly. So we just write it down like this.
I'm confused for a second. What's
Yes.
the U3V3?
If you do your vector U, it's U1, U2, U3. And the vector V is V1, V2,
Okay.
V3. So that's what that is. And normally what you do in this formula is that you replace that top expression and you just call it U dot V. So there is a formula that you can use to find the angle between any two vectors. It's the dot product, this guy, divided by the magnitude of this vector times the magnitude of this one. And I'm saying U1, U2, U3, and I apologize for that. We're only doing 2D. My brain was thinking.
Yeah, that's why I
3D.
was confused. It's like, where did the
Yeah.
V3 and U3 come from?
Actually, it does work in 3D. I'm doing it with my Calc 3, so that's where my brain was. They're doing the same formula, but they're doing it with 3D. But you only need to do 2. So that's our guy. Let's do it. Suppose I have a vector 1, 7. I have another vector -2, 5. And I would like to find the angle between those two vectors. Well, I'd find the dot product, which is When I do dot products, I don't actually write all this stuff down. I just remember it's multiply the x's, multiply the y's. In this case, it's -2 add 35. So I hope that's positive 33. So I need that guy. I also need to know the magnitude of u, which is the square root of 1 squared plus 7 squared, which ends up being the square root of 50. I need to know the magnitude of v, which is from here. So it's -2 squared plus 5 squared, which is 29. Even if you can simplify these ones, unless it's some simple like the square root of 25, don't even bother, because they're just an intermediary calculation. Because the guy we're going to be using is this fellow. So we have a dot product over this guy times this guy. So the cosine of the angle between them is the dot product, which is 32, over the square root of 50 times the square root of 29. If I know the cosine of theta is this ugly fraction, how will I find angle theta? I know the cosine of theta is this ugly fraction. What would I do to find theta?
The inverse cosine.
So if you want to do it in one big go, in other words, let the calculator handle it in one big go, that would do it. Oh, and by the way, the good news is with these questions, unlike the inverse tan, you know, sometimes the inverse tan gives you an angle that you can't use and you have to figure out which one it is. In these questions, you don't need to worry about that because the calculator gives you the angle you want, right? So every time it works without too much trouble. So inverse cosine, 33 divided by square root of 50 times square root of 29. And the answer is 29.9 degrees to 1 decimal place. Now, if you look at that calculation carefully, did you notice I put in some extra brackets? Here. Let's show you why that is necessary. Here is the inverse cosine, 33 divided by square root of 50. Oops. Where the heck did that come from? Divided by square root of 50 times square root of 29. Okay, hit enter. What's the problem? Looks the same, doesn't it? When you're doing it in your calculator, you need to put those two guys inside their own bracket. Why do you need to do that? Why do you need this inside its own little extra bracket? Okay, if I didn't do that, the calculator would think, okay, inverse cosine, got it. 33 divided by the square root of 50, got it. Oh, then multiply the answer by the square root of 29. Could you see that if you did that, you could get a number bigger than 1, and that's why it went error. So if you're ever doing one of these inverse cosine calculations in the dot product, will you please make sure that you stick this extra bracket around? Otherwise, you're going to get error every time, and you're going to think that you don't know what you're doing, when really it was just a simple case of doing it in the brackets, right? I'll do this calculation at the top without brackets, right? So 33 divided by square root of 50 times square root of 29. Right, that was a mistake because I hit the wrong buttons. So 33 divided by square root of 50 times square root 29. There we go. Do you see that answer is 25? Inverse cosine of 25 doesn't exist, right? There's no angle that has a cosine bigger than 1. And that's what's going to happen if you don't have the brackets. And that's a good time for us to finish. So last name and bye-bye. And I'll hang about for any questions.
I kept getting 38 instead of 29. I'm not sure what I'm doing wrong.
Well, are you in radians or are you in degrees?
I just put it back in degrees.
That's the right place to be. I should check that I'm in degrees then. No, I'm in degrees, so it's not that reason. Right, let's do that calculation again
Okay.
from the start. So in case it's me, inverse cosine, that's
Mhm.
easy to do. 33 divided by, start a bracket and then do these two guys. So it's going to be square root of 50, need to close a little bracket on it, times square root of 29, need to close its brackets and then close one more.
Times square root of 20. Oh, okay. I got it that time.
Right. But you can see how easy it is not to get the right answer when there are brackets inside brackets and some multiplying and dividing going on as well.
Yeah.
So it's a common mistake, so be careful.
Okay. Thank you.
You're welcome. Right, any other questions while we're here?